So, you've built a propeller-driven aircraft and need to set up its power plant. Today I'll be covering piston engines and propellers. Turboprops will be covered separately as they are a bit different to optimize, but the connection between propeller and engine is roughly the same as for piston engines. There's a lot to cover, so I'll put some timestamps on screen now. Before we get started, it is important that the correct fuel type is selected. Piston engines do not run on jet fuel. Use isooctane or avgas, otherwise you'll suffer from severe performance issues. To start off, there are three different layouts you can choose for your engines: radial, V, and inline. Note that if you want to make flat engines or X engines, you can use multiple inlines or Vs and link them to the same gearbox. One of the most important aspects of your engine is the power curve plot. This shows the power and torque curves at varying RPMs. You can also see how your engine's power and torque change with altitude. This plot is invaluable for determining the RPM the engine should operate at. A safe RPM value to use is where the power and torque curves intersect, as you will be guaranteed to have enough power and torque to keep the engine running. You can use an RPM higher or lower than this, but you may end up with too little power or torque, both of which will result in difficulties for powering the propeller. Next we have the cylinder type, which determines how the engine is cooled. Air-cooled engines rely on forward movement of the aircraft and ambient air temperature to keep the engine cold. Moving too slowly with these engines will not give any cooling, so it's important to not get too slow while at full throttle. Liquid-cooled engines use the radiator part to keep the engine temperature down. The radiators remain inactive until cooling is required. A larger radiator will be more effective at cooling, but will also be heavier. The rows setting changes the number of rows of cylinders your engine has. More cylinders will make a more powerful engine. You can also adjust the number of cylinders per row for radial engines. Next we have the bore and stroke. Bore affects the width of the cylinder, and increasing it will increase RPM and power. Stroke affects the length of the cylinder, and increasing it will decrease RPM and increase torque and efficiency. A decently performing engine will generally have values for bore and stroke relatively close to each other. The compression ratio is the ratio between the cylinder and combustion chamber volumes when the piston is at the top and bottom of its stroke. A higher value can generate power more efficiently and effectively, but too high of a value will lead to preignition or overheating in some cases. Valves affect how much fuel-air mixture can flow into the cylinder. A higher area will lead to a more powerful engine. Two valve systems are available for older engine designs. The supercharger is a form of air induction that uses some of the engine's power to compress intake air before it reaches the cylinder, generating more power. A higher supercharger pressure ratio will increase the amount of power generated by the supercharger. A second gear can be added to the supercharger, and it can be set to activate at a set altitude to give better performance at higher altitudes. Due to a bug at the time of recording, the power curve plot did not show the effects of the second gear. A turbocharger is similar to a supercharger, except it uses energy from the engine's exhaust gases to compress the air. Turbochargers are more effective at a given altitude, but are also heavier. Turbochargers are also more prone to inducing preignition, so use of intercoolers may be required. They also delay the engine's throttle response time for sudden large throttle changes. You can also use a supercharger and turbocharger on the same engine to make it twin-charged. This can help mitigate issues with the two individual systems, provided they are both set up correctly. Manifold pressure is used to get rid of excess pressure, which can cause preignition. As noted in the tooltip, this is useful for dumping pressure in high-density air. Do note that you can get a substantial performance increase if you raise this to just the right value, as seen in the background footage. Next we have idle throttle, which just controls the throttle percentage the engine sits at while idle. If this value is too low, the engine will sputter out and die while idling. Increase it to slightly above what is necessary to keep it running. Mixture controls the ratio of air to fuel entering the cylinder. A lower value will run more fuel rich and allows for more power up to a point. Too low and you will choke the engine. A lower value can also reduce preignition. A higher value will run leaner and is more efficient but will decrease power and can also increase preignition. A flywheel is used to conserve the engine's rotational energy and momentum by adding a rotating mass to the crankshaft. This will make the engine's power and rotation rate jump around less while it's operating, but will also make the engine assembly heavier. Before we go and test the engine, we need to add a propeller to load it. To do this, place a gearbox and make sure its power source is set to the nearest engine. The decimal number will indicate the distance to the available engines. Next, place a propeller on the gearbox and make sure its power source is set to the gearbox. As mentioned earlier, preignition occurs when the fuel-air mixture ignites before the piston reaches the top of its stroke and is harmful to the engine's performance. The red percentage value in the engine readout represents the remaining distance in the piston stroke when the fuel-air mixture detonates, and therefore a larger number is worse. Preignition is most often solvable by reducing the compression ratio or reducing the mixture slider. At higher altitudes, preignition becomes more prevalent even if your engine was not preigniting at sea level. If you have turbocharged or supercharged engines, which you probably should for high altitude flight, you can use intercoolers to help mitigate this. Intercoolers are made by switching the radiator part's function to intercooler. Be sure to select the target engine too. Intercoolers will only work when the engine is throttled up. Be sure that your engine is designed so that preignition does not occur while at idle or low throttles, otherwise your intercoolers will need to be very large and heavy to prevent preignition at higher altitudes. In addition to preignition, you also need to consider the engine temperature. At about 457 Kelvin, the engine will start overheating and then take heat damage. Heat damage will make your engine's performance deteriorate, and higher engine temperatures will make the damage level worse. Overheating is generally caused by high compression ratios and having an engine with a very high RPM. Liquid-cooled engines combat overheating with radiators. Once your engine reaches 400 Kelvin, the radiators will activate and start cooling the engine as needed. Larger radiators will be more effective, but will be heavier. The same goes for intercoolers. Air-cooled engines combat overheating by simply moving forward, so there is an influx of cooler air on the engine, lowering its temperature. If you're too slow at a high throttle, your engine will still overheat. A well-performing propeller generally spins with a tip Mach number of around 0.8 to 0.9 while at operating conditions. This is accounting for altitude and speed. Remember that the speed of sound decreases with altitude, so the higher you go, the higher your tip Mach number will get. I've made a calculator that takes your propeller diameter, rotational speed, aircraft speed, and altitude, and gives the tip Mach of the propeller under those conditions. The link is in the description. If your propeller spins slower than Mach 0.8 to 0.9, you may be losing out on some thrust, although this can be fine for making very early aircraft realistically. If the propeller spins too fast, it can also lose out on thrust due to the propeller airfoil reaching its critical Mach number and losing effectiveness due to the appearance of shocks. To provide ample power to the propeller, the engine also needs to be spinning at its own optimal RPM, as mentioned earlier. Because the engine and propeller are usually required to spin at different rotational speeds, we will need to adjust the gearbox's gear ratio. For aircraft, we only want a single gear. We can also leave the final drive at 1. The only setting we want to change is the gear 0 ratio. The gear ratio is simply the input rotational speed divided by the output rotational speed. Here's an example for calculating gear ratio. Let's say you have an engine whose ideal speed is 2000 RPM and a propeller whose ideal speed is 1400 RPM. Divide 2000 by 1400 and you get a gear ratio of roughly 1.43. Gear ratios for piston engines will generally vary from 1 to 2.5. For turboprops, gear ratios are much higher, usually from 10 to 20 or more. If you're going for an era-accurate plane, just note that a majority of aircraft from World War I or earlier used direct drives, so your gear ratio for these would be 1.0. If you can't get your propeller up to speed with your current settings, you likely need to decrease your propeller's weight by either decreasing size or blade count. Changing size will require you to recalculate your gear ratio. While designing a propeller, it is very important that the blades are generating thrust efficiently. The most useful metric to gauge this with is the propeller's angle of attack readout in flight. Here we can see the angle of attack of the root, midsection, and tip of the prop. We also have some colors to see how well each section performs. A white number indicates no stall and its respective section is working well. A yellow number indicates that the respective section is very close to stalling and is slightly inefficient. A deep red number indicates that the respective section has stalled and is generating very little useful thrust. In flight, we want these numbers to be very close to each other for the most efficient thrust generation, which brings us to blade twist. As the name implies, applying twist to a prop adjusts the pitch angle of a given section so that its angle of attack in flight is not too high or low. Because a propeller rotates, different sections along the span of the blade will experience a different relative velocity, which causes them to experience different angles of attack. The two components of this relative velocity are the tangential velocity of a given blade section due to the propeller spinning, and the axial velocity due to the aircraft traveling forward. By taking the arctangent of these two component vectors, we can calculate the blade's angle of attack at a given RPM, percent span, and airspeed. Fortunately, the game already does all this for us at the root, midsection, and tip in the prop's part window. In flight, the blade's angles of attack should be around 5 to 8 degrees for best performance when at normal operating conditions. Decent twist values for starting out are around 47 to 51 degrees for the root, 21 to 27 degrees for the midsection, and 0 to 6 degrees for the tip. You will likely need to change these as you test your plane. If a blade section's readout is negative while the others are positive, you need to increase twist of that section. There are different constant speed modes the propeller can be set to so that it doesn't spin too fast or too slow. To maintain RPM in these modes, the propeller adjusts its blade pitch automatically. I'll get to these in a moment, but first I'll cover the two other pitch control modes. The first is actually no control at all, and the blade remains at a fixed pitch. This means that the propeller can only be optimized to operate at one airspeed and will suffer at all other speeds. This is an ideal choice for early aircraft that did not have any form of variable pitch. To use this mode, simply set the constant speed mode to NA and adjust the blade twist to your liking. Regardless of the mode you use, I recommend reducing the fixed pitch slider to 0 so that you have no latent pitch on the prop that might induce unwanted angles of attack. The second is manual pitch control. This will allow you to adjust the pitch of the blade to your liking in flight and can be useful if the automatic speed modes are too sluggish for your needs, although it also requires the propellers be monitored frequently as speed and altitude change. The constant speed mode stays at NA, but you will need to create a custom input for pitch and assign a response to it in the propeller's pitch controller. You can also set up reverse thrust by assigning a negative response to the pitch controller like I did here with the brake input. The first type of automatic speed and pitch control is the target RPM mode. This will adjust the pitch angle of your propeller so that it matches the target RPM. If your prop is spinning slower than the target RPM, it will reduce the pitch, lowering the blade angles of attack, allowing it to speed up. If your prop is spinning faster than the target RPM, it will increase the pitch, raising the blade angles of attack, slowing it down. There are two things to keep in mind regarding the performance of your engine and propeller using this mode. If your prop cannot reach the target RPM at full throttle and isn't changing the pitch at all, your propeller is too heavy for the engine and you need to make it lighter by any means necessary. This can be done by reducing size, blade count, or blade chord. You also need some amount of twist for this mode to work. If your blade angle of attack readouts are all stalling when at full throttle, your prop is too light for your engine and needs to be made heavier. You may also just need to temporarily increase your target RPM. In flight, you can adjust your target RPM by holding 3 and 4. This is great for preventing your prop from stalling at low speeds, such as those encountered during takeoff. Next we have the centrifugal mode. The centrifugal mode adjusts the prop pitch based on its current rotational speed. Simply put, the prop will pitch more the faster it spins. The responsiveness value changes how aggressively the prop adjusts its pitch. A higher value will make the blades pitch more for a given RPM. The power value changes the linearity of the response. A higher value will make the blades pitch less at lower RPMs so they don't stall. In general, a higher power value will require a significant responsiveness value for the prop to be effective. Because centrifugal mode only adjusts pitch based on current prop RPM, it quickly becomes ineffective at higher speeds, even with high response values. Because of this, it is best suited to very low-speed, low-tech aircraft. Next we have the Mach response mode. This mode adjusts prop pitch based on the tip Mach of the propeller. Unlike the centrifugal mode, this also accounts for the forward speed of the aircraft. Similarly to centrifugal, the higher the prop's Mach number, the more it pitches. Because the prop's tip Mach number also depends on the forward speed of the plane, the propeller will increase pitch as the plane speeds up, similarly to the target RPM mode. This mode is competitive to the target RPM mode due to its ease of use and effectiveness, but the ability to adjust the target RPM mid-flight makes the target RPM mode the most effective for generating thrust across vast changes in speed and altitude. Next we have the prop settings, the first of which is the blade type. There are 5 blade types, each with different performance characteristics. The first option has elliptical blades, and I will use this style as a control group. As such, there isn't much to say about it other than the fact that it is moderately efficient at generating thrust. The second option has parabolic blades. Compared to the control group, it appears to be marginally less efficient at generating thrust. To compare thrust efficiency, I am looking at specific thrust and the angles of attack of the blades. Specific thrust is a measure of how much thrust a propeller generates per unit of power put into it, and therefore a higher value will mean the prop is more efficient at a given set of conditions. With angle of attack, however, if a propeller does not pitch as much as the control group to hold a certain RPM, we can assume its blades generate more drag than those of the control group, and it isn't as difficult for the prop to slow itself down to set target RPM. Therefore, we can infer that a lower angle of attack for a given RPM indicates lower blade efficiency. With those two aspects in mind, I'm only comparing these while stationary and at a specific RPM and gear ratio. There may be specific conditions at which some blade types are more efficient than at the conditions tested here. The third blade is the scimitar blade. It is more efficient than the control group, but has an additional property that makes it useful at higher speeds and altitudes. Because the blade is swept, it is more efficient at higher tip Mach numbers in the same way that a regular swept wing is. I'll get into this property more in the wings tutorial. The fourth blade type is squared off at the ends. Compared to the control group, it appears to be marginally more efficient. The fifth and final type is tapered. Similar to the scimitar blade, the prop had to stall itself to meet the target RPM, and the only way it could get it to the target RPM was by changing gear ratio and increasing blade count, diameter, and chord. And while the end result was a more efficient prop, it was also significantly heavier than the control prop. Next, we have the blade length and chord. Changing these will affect the blade shape, which will affect the aspect ratio and mass. Aspect ratio is a measure of a wing's or blade's span compared to its planform area. A blade that is very long and thin has a high aspect ratio, while a blade that is short and wide has a low aspect ratio. A high aspect ratio blade will be more efficient at generating thrust, but there is one benefit of having a lower aspect ratio. A blade with a lower aspect ratio will have a higher stall angle, similarly to wings. As a recap, I'll quickly go over the steps to setting up a prop for your engine. 1. Create the engine and add a gearbox to it. Make sure it's connected in the parts settings. 2. Add a propeller and change its size so it's appropriate for your aircraft. 3. Check your engine's RPM where the torque and power curves meet. 4. Using the prop Mach calculator I've linked, enter the propeller's diameter and altitude and speed that you will be flying at. Change the RPM until the tip Mach number is around 0.8 to 0.9. 5. Divide the engine RPM that you obtained by the number obtained in step 4, and set the gearbox's gear 0 ratio to this number. 6. Set the fixed angle in the prop to 0 from 35 degrees. 7. Choose the constant speed mode you want to use, if any. Change the settings accordingly. 8. Add some twist values to the prop. Make sure the root is the highest and the tip is the lowest. 9. Test fly the plane and monitor the prop. If the prop is too far below the RPM you want it at, it is likely too heavy for the engine and needs to be made lighter by reducing blade count, chord, or length. If the prop is too far above the RPM you want it at, and the blades are stalling at all sections, it needs to be made heavier. 10. Once the prop is at a decent RPM, make sure the blade angles of attack are all near 5 to 8 degrees in flight at the speeds you will be operating at most. If a section's AOA is too low, increase it, and vice versa. 11. Depending on the constant speed mode you use, you may need to adjust its settings for decent performance, although some modes may be fairly limiting. The final aspect of piston engines to cover is the exhaust. You can find the exhaust part in the Power tab. When set to an engine through its settings, the exhaust generates a small but not insignificant amount of thrust in the direction opposite to where the nozzles are pointing. Note that adding more exhaust will not increase the total exhaust thrust, but instead will distribute the thrust evenly across the exhaust parts.